All right, y'all. So I'm just going to make a quick video kind of reviewing over this unit. So before I start the review, just kind of making sure y'all see this, this schedule. So remember that this calendar is always on the front of your notes, okay? So if you ever have any question of what we're doing that day, what we've done that day, what PCLs are open that day, these are always going to be on the front of your notes, okay? And so we have done properties of light and light calculations. We've done Bohr's model of the atom. We've done quantum numbers and introduction to electron configurations. We've done electron configurations and orbital diagrams. And then we've done periodic table trends, okay? And the periodic table trends, these are what you were supposed to do yourself, okay? And then today you're going to be doing the test review, so you'll watch this video, and then you will you'll work on your practice worksheet and the Canvas PCL that's open. Now, I'm going to introduce polyatomic ions at the end of this video, but you're going to be doing polyatomic ion memorization. And so we're going to, at the end of the video, I'm going to kind of talk about that, okay? So now let's kind of go over, let's touch on some stuff that we've kind of done, okay? So we first started off by talking about light and about how light can be a wave or a photon. It can be, there's a particle wave duality to it. We've talked about wavelength and frequency. So wavelengths is the distance between the crest or the trough, and frequency is how many wave cycles that can pass a certain point in a second. And so the smaller the wavelength, or the shorter the wavelength, the higher the frequency. So the shorter the wavelength, the more waves can pass a certain or given point. We talked about the speed of light and the energy of light. So the speed of light is 3 times 10 to the 8th meters per second. Now, so make sure you understand that it's meters per second and not nanometers per second. So there may be some conversions you'll have to do. Energy of light is the power, or how much light that how much power that light has. Now remember that energy and frequency are directly related, but wavelength is indirectly related to energy. So here we have all the different forms of light from radio to gamma. Now this is different than your notes, I think. But so we have radio waves is our biggest. It has the longest wavelength. Therefore, we have a lower frequency and a lower energy. And as you decrease your wavelength, your energy is going to increase. So gamma radiation is the highest radiation. Now remember, you do need to know all of these different radio waves. So a good way to remember it is red men in Virginia use X-ray guns. Okay? And so red is radio, men is microwave, N is infrared, Virginia is visible light, U's is ultraviolet, X-rays is X, and then guns is G. Okay? Now remember that there is an inverse relationship between wavelength and frequency, a direct relationship between frequency and energy, and an inverse relationship between wavelength and energy. Okay? Now remember that these are different formulas for the light waves and the constants that go with that. So our constants are the speed of light, which is 3 times 10 to the 10 to the 8th meters per second. And then Planck's constant is 6.63 times 10 to the negative 34th joules times second. And so we can use these formulas to calculate an example. Now I'm going to do just a couple, I'm going to pull a couple of examples from your practice worksheet just to kind of go over them. So number 15 says find the wavelength in nanometers if the frequency is 4.1 times 10 to the 11th seconds to the negative 1. So we're trying to find wavelength when we're given frequency. So the best formula we can use is our speed of light. So speed of light is wavelength times frequency. And so if you were to get wavelength by itself, it would say wavelength is equal to the speed of light divided by frequency. Okay? And so remember, the speed of light is 3.0 times 10 to the 8th meters per second divided by our frequency, which was given as 4.1 times 10 to the 11th seconds negative 1. Okay? Now, when we calculate this, remember what you're going to get is going to be in meters. Okay? So we do 3 times 10 to the 8th. I'm going to put it in parentheses. 3 times 10 to the 8th divided by 4.1 times 10 to the 11th. And that's going to give me 7.3. I'm going to do sig fig, so that's going to give me it should be 7.3 times 10 to the negative 4th. Now this is meters, okay, but we need it in nanometers. So to convert, we do 7.3 times 10 to the negative 4th meters. Okay, and our conversion is that in 1 meter, there's 1 times 10 to the 9th, or a billion nanometers. Okay, and so if we do 7.3 times 10 to the negative 4th, I'm just going to do the answer, times 1 times 10 to the 9th. That's going to give me 731,707. And if you convert that to scientific notation, it's going to be 7.3 times 10 to the 5th nanometers. Okay? So that's how we would get 7.3 times 10 to the 5th nanometers. Now the next question says, how many joules of energy are there in a photon of light whose wavelength is 6.3 times 10 to the negative 7th meters? Okay? So looking at these formulas, I can actually use this one, which has Planck's constant, speed of light, and wavelength to calculate my energy. Okay? So we're going to say energy is equal to Planck's constant times the speed of light divided by wavelength, because the speed of light divided by wavelength is going to be frequency. Okay? So our energy is going to equal Planck's constant, which is 6.63. I'm going to do E negative 4 joules times seconds times the speed of light, which is 3.0 times 10 to the 8th meters per second, divided by our wavelength, which is, and notice our wavelength is already in meters, so we don't have to convert to meters before we use this. Our wavelength is 6.3 times 10 to the negative 7th meters. Okay? So when I calculate this, I'm first going to do 3E8 divided by 6.3 E negative 7. Okay, and then I'm going to do that number times Planck's constant, 6.63 E negative 4. And that's going to give me, well, let me try that again. Okay, let me double check and make sure everything's in the right place. We got Planck's constant, speed of light divided by, oh, I know what it was. It was 34. Well, see, common mistakes, Okay, so let me try this again. 3E8 divided by 6.3 E negative 7. Okay, and that's going to be times 6.63 second E negative 34. There we go. And so we're going to get 3.2 times 10 to the negative 19th, and our unit is joules. That joules comes from Planck's constant. Okay? All right. Now moving on, we're going to review over the Bohr atom and light. So remember that Niels Bohr used light to determine that energy, or that electrons are separated into energy levels. So these electrons will absorb energy in the form of light or heat. They will jump energy levels. And when they jump back down, because they're not going to stay up there, they're going to crash, or what we call, they're going to relax. When they jump back down, they're going to emit light, and this light is what we see as color. So during our flame lab, we saw that the different flames were different colors. So when electrons gain energy, this is called excitation or absorption. And when they lose energy, this is called relaxation or emission. So this is how Niels Bohr found out that the atom was separated into energy levels. And So what they also did is they took this tube, so they ran an electrical current through a tube of hydrogen. They concentrated that light and ran it through a prism, and they saw that it made these lines. And this is what we call a bright line spectra, or an emission line spectra. Okay, each element has its own line spectra, and this is kind of how electrons, or how we can tell the difference between different elements, is from their line spectra. So it's like a fingerprint. Okay. Now, moving on to quantum numbers. Okay, so remember quantum numbers. In quantum mechanics, we have energy levels, we have sublevels, we have orbitals, and we have electrons within those orbitals. Okay, so remember, this is how the electrons are organized. Now, you're going to need to know those 4 quantum numbers and what they're called, the principal quantum number, etc. But I'm just going to kind of go over each energy level and the sublevels that are within them. So we have our energy levels. Each energy level, as they get further away from the nucleus, they're going to increase in number, and they're also going to get bigger. So each energy level, as you get further away from the nucleus, is going to be able to hold more sublevels. Okay? So the first energy level has the S sublevel. Now remember, the S sublevel only has 1 orbital, and that 1 orbital, so each orbital can hold 2 electrons. That's why the first energy level only has 2, because it only has that S. Now the second energy level has an S and a P. There's 2 in the S. Now the P, remember, have 3 orbitals. That's why there's 3 lines. Each orbital holds 2 to make 6. So there's 2 in the 2S, 6 in the 2P, total of 8 in the second energy level. Third energy level has an S, P, and D. So 1 orbital for the S with 2 electrons, 3 orbitals for the P with 6 electrons, 5 orbitals with the D with 10 electrons. Okay, so there's 2, 6, 10, and that's going to be a total of 18. And then the fourth energy level has 2 in the S, 4 in the P, 6 in the P with 3 orbitals, 5 orbitals for D with a total of 10, and then 7 orbitals for the F with a total of 14. So that gives me 32 electrons in that D sublevel. Now remember, we can use the periodic table. Okay, we can use the periodic table to organize these electrons. Okay, so we have our energy diagram. So remember, as energy increases, you're going to fill in these electrons as energy increases. So remember the different rules. That's the off-ball principle. The off-ball principle is the lowest energy amount first. Now remember, it doesn't always fill in by first energy, second energy. Okay, remember, it starts to get weird, because as we start filling these in, we fill up the 3P, and you'll notice that in this increasing energy, the 4S is actually lower than the 3D in energy. And so that's why what's going to happen is we're on the third energy level here. We're going to fill in that 3P, we're going to jump up to the fourth energy level, fill in the 4S, and jump back down to the 3D. Okay? And we're going to use our lines and arrows to do that. Now on our periodic table, that's given by going after the 4S, you're going to go down to 3D and back up to 4P. So remember, you can use the periodic table like a game board, right? So if you're trying to get to cobalt here, you're going to start with 1S, 2, and then 2S, 2, then 2P, 6, and then 3S2, 3P6, 4S2, and then you're going to count 3D, 1, 2, 3, 4, 5, 6, 7. Okay, so you're going to have 7 inside the cobalt. Okay, and so you're going to be able to answer these. These are just talking about the energy levels and the sublevels. These are talking about what's wrong with each of these figures. And then here's the electron configurations. Now remember, electron configuration notation, orbital notation has the lines and the arrows. It shows the different numbers of orbitals. Electron configuration notation does not need the lines and arrows, okay? So all that it shows is how many electrons are within that sublevel, okay? And so with these, you will have, you will just write the superscript to show how many electrons are within the sublevel, okay? So we're just going to look at one example of this. First one says, write the complete electron configuration, okay? So we have selenium. Now selenium on the periodic table, if you look, selenium is going to be right here. I'm not going to count over. Okay, selenium is going to be right here. Okay, so that is our goal. So when we're writing our electron configuration, we're always going to start with 1s. We're going to count 1s, 1, 2. So I'm going to write 1s, 2. And then keep moving. 2s, 1, 2. Now remember, every time you hit a new row, you're starting a new energy level. And then every time you hit a new block, so we go from 2s to 2p, 1, 2, 3, 4, 5, 6, you're going to hit a new sublevel, 2p6. Then 3s, 1, 2. So 3s2, go over, 3p, 1, 2, 3, 4, 5, 6, 3p6. Then we're going to do 4s, 1, 2. Okay, 4s, 2. And then remember, it goes from 4s to 3d. So you're going to count 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d, 10. And then 4p, we're going to selenium. 1, 2, 3, 4. Okay, so that's going to be 4p4. Now it says construct the orbital diagram. Okay, so that means with these, I have to draw the orbitals also. So remember, from 1s, s has one blank, and so I'm going to draw two arrows. 1s, there are 2 electrons within that 1s. Next is 2s, again it's an s, so I draw one blank with 2 arrows. Then 2p, the p have 3. So 2p, we're going to fill in. Now remember Hund's rule. Each blank gets an electron before any can get 2. And then move on to 3s, 2. Now p again is 3 blanks, so 3p, go across. Then 4s, 2. Then 3d, so 1, 2, 3, 4, 5. 3d has 5 blanks. Okay, so each blank gets 1 before any gets 2. And then 4p, and it's going to be 4. So again, this is where you have to follow Hund's rule. Each blank gets 1 before any blank can get 2. You do not put 2 in the 2 first ones. Each blank has to get 1. Now it says, what are the highest energy amount electrons? Now remember, the highest energy amount electrons are the last sublevel filled. So the last sublevel filled is the 4p4, okay? So that means those 4 electrons in the 4p are the highest energy. Now the outermost valence electrons are the electrons in the highest energy level, okay? The highest energy level, while they did fill out of order, would be the 4s and the 4p. So 4s2, 4p4 are my valence electrons. And it says how many valence electrons are there? There are 6 valence electrons, okay? Now, how many unpaired electrons does the element have? So you got to look at your last part of your orbital diagram, and we see that we have 2 unpaired electrons. What is the most likely ion for selenium? So it has 2 unpaired electrons, okay? It has 6 total valence electrons, so to get 8, it's going to gain 2 electrons to make a charge of -2. Okay, it needs 8, it's got 6, so it'll gain 2. So we are gaining 2. What would the new complete electron configuration be for the selenium ion? Well, if we gain 2 here, it would no longer end in 4p4, it'll be 4p6. So 3s2, 3p6. 4s2, 3d10, 4p6. Would the resulting ion be larger or smaller? Since we gained electrons, it's going to be larger. Okay, larger. And it says, which noble gas is the selenium ion isoelectronic? Okay, so remember what isoelectronic means? It means it has the same electron configuration. And so here it ended in 4p6 now. That is krypton's electron configuration. Okay. So now we're going to kind of skip forward. And let's talk about periodic table trends, okay? Periodic table trends. Now remember, before we skip there, remember these board diagrams and how to draw these, how to make sure what the highest energy electrons are and the valence electrons are. And just remember how to do that, okay? Now let's talk about our periodic table trends, okay? The first periodic table trend we're going to talk about are the atomic radii. Now atomic radii is the size of an element, okay? Atomic radii is the size of an element. Now you were supposed to fill in these notes yourself, okay? I'm not going to fill in the notes, but I am going to kind of review over what those trends look like. So atomic radii is the size of an atom, okay? So let me use this little periodic table. Now, as you go down a group, the atomic radii is going to increase. That means it's going to get bigger. The reason it gets bigger is because you're adding energy levels. Okay, you're getting bigger, you're adding energy levels. Now, for atomic radii, as you go across a period, it's going to get smaller. Okay? It's going to get smaller as you go across a period. And this is because of what we call the effective nuclear charge. That means that we are adding protons as we go across. So as we go across, we have the same number of energy levels. All the elements on the second row have 2 energy levels, but we're adding electrons, which kind of gives it more pulling power, okay? Think of it getting stronger. It's pulling those energy levels in more. Therefore, they are getting smaller as you go across a period, okay? Now, again, make sure that you are doing, these are the day 5, the notes that you have to do yourself and answer those questions, okay? And you're going to use the chart that's in the back of your notes to do that, okay? Now, so that's atomic radius. Now, if we were looking at atomic radii trends, we would know that the largest, if we're looking at trends, the largest element would be francium, okay? And the smallest element would be helium. Helium has 1 shell, but 2 protons to pull that shell in. It makes it small. Here, francium has 7 energy levels, okay? But it has the least amount of protons out of everyone on the 7th period, and so it's going to be have a lot less pulling power. It's already having to pull a whole bunch in, and so it's not going to have that much pulling power. Now, ionization energy, okay, ionization energy has to do with the energy to pull. How much energy does it take to pull the first electron? Okay, that's called the first ionization energy. When you get into AP, you talk about second ionization energy, meaning how much energy is it going to take to pull the second electron. But to pull the first electron is the first ionization energy. So amount of energy required. So think of trying to take candy from a baby. It's easy to take candy from a baby. Now, if you're trying to take candy from Dwayne "The Rock" Johnson, it's going to be a little bit harder, okay? And that is the trends that we see as we go across a period. Ionization energy is going to increase across a period because we're adding protons. It's getting stronger. So over here, you've got the baby over here who's not holding on to its electrons as hard because it doesn't have as many protons as over here, okay? Our protons over here, they got a lot of protons. They're easy to hold on to, so that's going to be Dwayne "The Rock" Johnson. He's holding on to them really strong. Now, as we go down a period, ionization energy is going to decrease because we're adding those energy levels, right? They're getting bigger. My valence electrons are further away from that nucleus, okay? So it's going to be easier for me to take an electron, say from barium, than from calcium. Because calcium has 4 electron shells, whereas barium has 6, okay? So it's going to be easier to take an electron from barium than calcium. Okay, so that's ionization energy. Okay, ionization energy, the amount of energy required to take an electron, okay, to pull an electron. Now, the last one we're going to look at is electronegativity. Okay, electronegativity is the pull to gain an electron. So if ionization energy is taking electrons, so how much energy does it take to take an electron? Electronegativity has to do with the pull of electrons, so pulling the electrons closer to itself. Okay, think of ionization energy taking, electronegativity is pulling or gaining. We'll put gain electron. Okay, so as you go across a period, electronegativity is going to increase. Okay, electronegativity increases. Now again, it's because of those protons. Your effective nuclear charge is getting bigger. As you go across a period, you're adding more protons. Therefore, it has more pulling power. It's getting stronger. It's able to pull electrons. Now, as you go down a group, it's going to decrease. Okay, my electronegativity is decreasing as I go down a group because I'm adding those energy levels. Down here, my valence electrons are already really far from my nucleus. It's going to be harder for me to pull another electron from somebody else. Okay, whereas up here, I got a lot of protons. My electrons are really close to its nucleus, and so it's going to be able to pull an electron really easily there. Okay, and so those are the three, just kind of a glance over the three trends. Again, you are having to fill those notes in by yourself, so that's another thing you can do today is if you did not fill those notes in for periodic table trends, you need to fill them in. It is very important that you do so, okay, because you're going to see those trends a lot in AP Chemistry, okay. One last thing is polyatomic ions, okay. So at the beginning of the school year, I gave you 2 orange sheets. I gave you a little one and a big one. So here is our big sheets that I gave you. These are our polyatomic ions, okay? So you got perbromate, you got periodate, perchlorate, nitrate, bromate, carbonate, iodate, chlorate, chromate, sulfate, phosphate, nitrite, bromite, iodite, chlorite, sulfite, phosphite, hypobromite, hypoiodite, hypochlorite, hyposulfite, okay? And then we have others down here. We have permanganate, we got acetate, we got hydrogen carbonate or bicarbonate, like sodium bicarbonate, like baking soda, dichromate, hydroxide, cyanide, and then ammonium. Ammonium is the only one here that has a positive charge, okay? So we are going to start taking quizzes on these polyatomic ions, okay? Our first quiz, it's going to be just like our, what's it called? Our elements, okay? So our first quiz is polyatomic ion, PLC. It's going to be a PLC, okay? And that's going to be October 19th, okay? Our second PLC, polyatomic ion, PLC. Now, our first PLC is going to be the first 2 columns, okay? Our second PLC is going to be all 4 of these columns. So first 2 columns and then all 4, and that's going to be the 25th, October 25th. And then our polyatomic ion, AOL, is going to be all 4 of these columns plus these on the bottom, okay? And that is going to be on November 2nd, okay? So that's when all of those are going to happen. So please make sure that you are studying these right now. You should have this sheet. If you don't, come see me and I can give you another one, okay?